Yeah, well, anyway, thank you very much for the opportunity to speak to you all about this subject. So I just want to start with a few general remarks. So it's about integral geometry. So integral geometry is a slightly, I mean, in some way it seems it has been sort of a peripheral subject in mathematics. I'm sort of devoted to it, and I of course feel that it's actually quite central. So the past 10 or 15 years have seen a lot of activity in integral geometry, although the focus has been less on geometric measure theory aspects, but rather more on ways in which, in fact, in a surprising way, algebra enters in an important and penetrating way. These talks, however, I want to talk about the geometric measure theory aspects. It is definitely a subject of integral geometry of geometric measure theory. It's not one that's common. So in some way, it is. Here we are. I mean, this where are we? Doesn't exist yet. Can I get some help? So anyway, so this it's part of this. There's a certain aspect of the subject which is very heavily measure theoretic, geometric measure theoretic. It's sort of unusual in the sense that it has so far nothing to do with the calculus of variations, but everything to do with the theory of integral currents. Oh dear. So my intention here was to appeal to authority somehow and make the case that this really is a central part of geometric measure theory. Is this going to work? Maybe we should renew this. Okay, doesn't matter. What happened? There we are. Very good, very good, very good. Let's see if I can do that. There we go. So forget it. Forget it. I'm going to just give up on this one. So the point is, this subject is, somehow the modern era in the subject goes back to Federer. Oh dear, can we cut this off? Sort of inauspicious beginning. Thank you. Yeah, so somehow this whole subject revolves around eraser. Here we are. Yeah. Revolves around the so-called Principal Kinematic Formula. Okay, so what is the Principal Kinematic Formula? So it says the following thing. So if you have a couple, the classical version says the following. So you have a couple of subsets of Rn, say they're compact and nice. Well, in fact, I'm not going to tell you exactly what I mean by nice. In fact, in some sense, that's the entire issue. And I'm not going to give you a definitive solution, the definitive answer to what this word means in this context. In fact, that's sort of an ongoing mystery. I intend to lay out aspects of this mystery as we go. But anyway, under these conditions, one can look at the intersection of these two bodies in every possible relative position. I'm going to take G bar to belong to what I call SON bar. This is the Euclidean group, say the oriented Euclidean group. And I'm going to integrate this over that group with respect to Haar measure. And it turns out that this integral is always expressible as some bilinear form in certain quantities that are attributable to the bodies individually alone, maybe with some coefficients. Here like that. Okay, so again, the question of what these coefficients are is interesting, I would say, but we're not going to address that too much. That belongs to the algebraic side of this subject. Rather, we're going to think about the question of, well, if we look at this integral, this quantity that we're integrating, clearly makes sense under quite general conditions. For example, the most classical form of this formula is when A and B are convex. That's one answer. That's one characterization or one version of this word nice. Federer's paper has to do with the case where these guys are so-called positive reach sets. Another case has to do where these are smooth domains bounded by smooth hypersurfaces. And in fact, these quantities mu I, so what are they? So again, those come in another nice way. Comes from Steiner's formula, at least which has again several different versions. So if we take, say, A sub r, which I define to be the set of all points where the distance from A is no greater than r. So here's some body, let's say it's convex. So here's A sub r out here. So the volume of this thing is always given by a polynomial of degree n. Again, maybe I'll put some other constants. Generic constant C, different constants perhaps. Mu I of A, r to the n minus I. So again, it's a polynomial of degree n in the radius here. So this is Steiner's formula. It's a beautiful, very simple formula. I was just explaining it to an old college friend of mine the other day. It's at the most basic level. It's for polygons in the plane. You can explain it to your mother. You can say, look at, if you look at the tube of radius r, this tube of radius r decomposes into pieces. Well, I guess there's the body itself, which is a piece of degree 0 in some sense. Then there are these triangular pieces which are some sense of the pieces of degree 1. Their total area is clearly the perimeter of the object times r. And then there's a final term which comes from these circular sectors. If you fit them all together, they make up a circle of radius r. And so in this case, the quadratic term is just pi r squared. So in this is somehow the very humble beginnings of this subject. So again, these quantities here and these quantities in the kinematic formula are identical. So yeah. So, but anyway, the point is, so this is I guess if A is convex, this is true. And if A is positive reach or smooth or something, then this is true, say, for sufficiently small values of r. And then there's a version, we'll see, which extends also to large values of r, but we'll get there. Okay, so as I say, somehow the sort of direct appeal, I think to me it's a very sort of an irresistible question. If you look at this integrand, as I say, if you have some maybe very, very singular bodies A and B, you could put them in here. Maybe one could expect that this integrand would be well defined for almost every position, and so the question is, under what conditions, under what regularity conditions on A and B is this formula valid? So basically that is sort of the So that's one version of the subject of these lectures. So as I say, even though this is not really a subject, yes.
What are the mu i's?
So the mu i's, you can view them as coefficients of this tube formula, if you like. Okay. So I'll be talking more about them throughout this lecture. Okay.
CI
Yeah. These are some coefficients. Yeah.
CI are coefficients as well.
Oh, so these depend on A. These are universal. Okay. Likewise here, not the same necessarily, but You'll forgive me. Okay, further questions? Yeah, thank you. Okay, so yeah, and as I say, this question, I think, to me, it sort of is just, I mean, somehow it just takes the lid off a very large can of many messy but beautiful worms. And so one of my intents here again is to lay out a number of open questions. Some of them may have embarrassingly simple answers. Some of them may be impossibly difficult. I'm not sure I know the difference between them, but we shall see. Okay. So yeah. So let's. I want to start to set the stage for this principal kinematic formula, this PKF. So let's start with Steiner's formula. Yeah. So maybe I should mention also the name of Hermann Weyl. So sometimes this is called the Weyl tube formula. If A is a smooth, compact submanifold, then this is again true for small values of R. As I say this, there are many other mysterious aspects of this subject. Okay, but let's begin with a certain view of this thing. So I want to understand better about what these functionals mu I are. So let's again take A to be something rather smooth. Say let's take A to be some smooth domain. And what we can do is as follows. We start with this object A. I want to express a small tube around it, A sub R, in a certain fashion. Well, this A has a certain normal field. I'll call it N sub A. And so this region, A sub R, can be expressed in the following way. Let me introduce a mapping, epsilon of x and t. So here x belongs to the boundary of A, and t is a real number. And so epsilon of x and t is just x plus t times the normal of A at x. So in other words, you start here at x, and you run out here to t units, and NA being the unit normal. So in other words, NA is the Gauss map of the boundary of A. So this is one. So what do we know? So then A sub R, at least the part of A sub R that's not in A, is just the image of the boundary of A across, say, this interval here. Okay? And if R is small, say some number, let's not worry too much about what the number is, then this epsilon, say, restricted to the boundary of A crossed this interval, is a diffeomorphism. Okay, so one nice approach to computing this boundary, to computing this volume, is as follows: is simply to use advanced calculus, the area formula or the volume formula. So the volume, let me use this, the volume of A sub R minus the volume of A, which of course is just the volume of of this little difference here, I can write as the integral over the boundary of A cross, say, 0R of the pullback of the volume form of Rn under epsilon. Okay, pretty simple. Okay, as long as it's a diffeo, that's fine. And now the question is, well, what is epsilon star of the volume form? We can easily expand it as follows. Let me change this notation. We call these y's. So here, I guess yi, I can think of as being xi plus t times the ith component of the normal. And so in this fashion, this thing clearly pulls back. Well, what is it? It's going to be some expression, some differential form involving differentials of the xi's, together with some quantities involving the second fundamental form A. In other words, derivatives of this. So what is it? So it's going to be dxi plus t n ai of x, etc. Okay, so what are these? So, I mean, in the end, what's the point? So in the end, we're going to integrate this thing over this object. So in order for that to persist, we need some dt's coming out in the formula. So what do we get? So we get dxi plus, say, dt times na I of x plus t times d na I of x, and so on. Okay. So the upshot is, if you start expanding this thing out and observe, as I say, that these things here can be expressed in terms of the second fundamental form of the boundary, what we get is that this is some polynomial. Let me put an equivalent here. I'm going to drop the, well, what's the point? As I say, in order to integrate, the only terms that contribute to this integral are terms that involve a dt. So we pick up this factor here. So what we get is some sum of, turns out, let me see if I can get this right. I probably won't. So t to the n minus I minus 1, sum from I equals, say, 0 through n minus 1. I'm going to look at the n minus I minus first elementary symmetric function of the principal curvatures of the boundary of A. Okay. And so what's the upshot? The upshot is when we integrate this up, then what we find is that mu sub I of A is, again, up to a constant multiple, the integral over the boundary of A of this quantity here, the perimeter of A. Okay? So these are these classical curvature measures. You know, this is somehow the, you know, if you read, yeah. So I apologize. I didn't get the my references into Hervé in time for them to be put up on the website, but I do intend to give you a list before long, perhaps even tomorrow. Okay. So you might look in the book of Saint-Lô, for example, on integral geometry, and this quantity appears. So this is a very extremely classical geometric construction. Okay. Does this go up? No. Does it go down? No. Oh, look. I get it. I think. Very good. So this is obscured permanently. Okay. Sorry? Is there a way to raise the back one? No. Okay. Yeah. So forget all that. So let's fast forward a little bit and okay. So well, let's not. Let's just do the following. Yeah. So. So if you look at that last picture, I'm afraid actually you do need to remember it, so bear that in mind. If I put that up, you want to take pictures with your smartphones and you have to look at, but maybe not. Okay, so there's also another way. There's another way to view this thing, which is for us critical. Okay, so somehow we want to take the same picture, only look at it. Well, okay, a little bit differently. So rather than look at the boundary of A, let's look at what I'm going to call n of A. This is the manifold. It's basically the outward unit normal manifold. Okay, so it's a graph of the Gauss map, if you will. So clearly, this is a diffeomorphism here. And now there's this mapping. So this guy here lives inside what? Lives inside the sphere bundle. So I'm going to call SRN. Like so. Okay. Now, I just want to, as I say, universalize this picture a little bit. What I want to do now is look at a certain mapping from this space, which I'll call the exponential map because, I don't know, I think it is the exponential map, but Bill Allard gave me a really hard time about that one time. He would not be assuaged, but whatever. So, in fact, maybe I want to take SRN cross R again. Here's the map, so I get x, v, and t is going to go over to x plus tv. So x now maps, mixing apples and oranges here. This is Rn, so x, v, and t goes like that. Okay, and so now, by the same token, if I look at a sub r with a removed, I can view this as now exp of n of a cross 0 r. It's just somehow some slightly universalized, some fancy, maybe stupidly fancy version, if you will, of the picture I wrote before. The advantage, however, is that this object here, this little setup here is, as I say, is completely independent of A. Okay, and now what we find is the following: if we take the pullback of the volume form of Rn here, now I can express this in terms of some kind of universal forms on SRN, like so. So it turns out that this thing has the following form. It has terms of two types, some involving dt. Those are the ones that count, so to speak, when we integrate. And then there are also other ones that involve a certain one form I call alpha. Alpha is the so-called contact form of SRN. So alpha, so it's a one form on SRN. So what is it? So at a point x comma v, yeah. So strictly speaking, I guess it's a pullback from SRN, if you will, but I won't distinguish. Okay. So this guy here. So this is a one form, and if I pair it with a vector, I guess a tangent vector at xv to SRN. So let's say it has the form tau sigma. This guy here is a tangent vector to Rn at x. This guy is a tangent vector to the sphere at v. This pairing is defined to be precisely just the dot product of v with tau. So in other words, the picture is as follows. Here's v. This one form, this one form measures somehow infinitesimal displacements inside the sphere bundle. So it's like an arrow, and so a tangent vector to the sphere bundle is such an infinitesimal displacement. Alpha assigns a number to it. So I think of this arrow, maybe the base point moving a little bit, and maybe this thing rotating slightly in some infinitesimal fashion. This one form just forgets about the rotation altogether and just measures the extent to which the base point moves in the direction of the point, so to speak, the point upstairs in question. Okay? Are we okay with this? So this is a so-called contact one form. It's actually a hugely important figure in this although not terribly subtle, but central figure in this theory. So if there are any questions, please ask them. Okay? All right. So I'm not done here. We'll get there in a minute. While I'm on the subject of alpha, let me just take note that if I look at the restriction of alpha to n of a, so here's a, so if I look at n of a, so this vector v is now just varying along n of a, you'll notice that if I displace this vector while remaining within n of a, well, this base point moves tangentially to the boundary of a, and therefore orthogonally to v. So this restriction is identically 0. So restriction identically 0. So in the world of contact geometry, we say that n of a is Legendrian submanifold. Okay? Okay, so in some sense, I think it's, if I understand some of the roots of contact geometry, might even be some sense the prototype of all Legendrian submanifolds. Okay, anyway, so back to the subject at hand. So what do we have here? So this guy here, this guy here is an n form. So I need to put an n minus 1 form here. So what I'm going to get is something of the same type. So I'll have the sum from I equals 0 through n minus 1 now. They'll again be, say, constant factors, scalar factors like that. And then I like to call these other guys kappas, kappa n minus I minus. I'm mixing up the indices, as I will do. So but here I think I'm getting it right. Okay? Okay, so these, yeah. Okay, so that's that. So what? So now, yeah, and maybe here I think actually you get almost exactly the same thing. However, from the point of view of the tube formula, this term, as I say, matters not at all, because when I integrate, well, for two reasons I might say. So first of all, there's no dt factor in it. When I integrate, oh, I didn't write that, did I? Let me write it down, especially since I covered up the other formula. So now I could write this volume as the integral over n of a cross 0r of x star of d vol. Okay, so now again, exp restricted to n of a cross 0r is a diffeo to ar minus a. And so this follows from the volume formula. And then after introducing this expression, we get this. Okay. All right, and at the end of the day, what happens, so when we integrate the t, we get something like 1 over n plus I guess, times the integral over n of a of kappa I, like so. Okay, so that's sort of this universalized picture. These guys here, as I say, are these universal guys. They just come out of this pullback from this universally defined map. So what are these guys? So these kappa i's, I should tell you a little bit about them. So what are they? They are n minus 1 forms in the sphere bundle. Okay, and because everything in sight here is Euclidean invariant, these guys are also Euclidean invariant. Okay, they're also Euclidean invariant. So again, these guys are a little bit funny looking. I mean, again, so all I've done so far is just sort of fancify everything, try to get my PhD or something. And but actually, as I hope to make this clear that this is an important kind of construction. But let's say a little bit more about what these guys are, as I said. So what are they? So kappa 0 maybe is and kappa n minus 1, they're both fairly simple. So at a given point in the sphere bundle, maybe it's convenient, as I say, because of invariance, it's convenient maybe to take v to be some special vector like the North Pole. Let's call it En. Okay. So let's start with this guy. So the kappa n minus 1 at xen just turns out to be, well, dx1 through dxn minus 1, or you could also say x star d vol, and you contract against En, if you will. Okay? So what is this guy? This guy here is, well, let's see, we have coordinates x and v. V is a spherical coordinate. Well, okay, so we have n of them, of course, even though n minus 1, sphere is only n minus 1 dimensional, but we can still think about the dv's. So in this case, this is just the pullback. Maybe I'm mixing up my spaces here, but it's the pullback of the volume form of the sphere under the sphere bundle, under the Gauss map, excuse me. Okay? And then what happens in between? Well, somehow in between you sort of mix and match these guys. So I guess this guy is going to have, if I put 1 here, it's going to have, what is it? So I put like -1 to, oh, sorry, I don't need that, do I? So I need something like this. So I'm going to take dx1 wedge dv2 all the way out to dvn minus 1. Okay, in other words, I take this guy, I start mixing in x's one at a time. And I guess I'm going to get n minus 1 terms of that type. Okay? Let me not try to write down kappa 2. Kappa 2, well, I'm going to take 2 dx's at a time, mix them in all possible ways, may throw in the appropriate signs, and that's what we get. Okay? It's just a direct calculation, actually. Okay. So so where's the geometry? So the geometry is still here. So these dv's, of course, well, when I pull them back, you know, if I, what do I do? I take boundary of A and I map up this way, and then I look at the pullbacks of these kappa i's, you know, pulled back all the way to here. These dvi's are just derivatives of the Gauss map. These things are just, again, some fancified way of writing down the elementary symmetric functions of the principal curvatures in some sort of universal fashion. Okay? All right. So which brings me to the first sort of inspiration of this subject. So as best I can tell, the history is a little bit murky. This idea was originally due to the late Peter Vinken, maybe 1983 or something. I learned about it from the papers of Martina Zela. Found it independently. There's also at least one nice paper on this subject by Jeff Cheeger, Werner Müller, and Robert Schroeder. But maybe 85 or so. Okay, so what is this inspiration? The inspiration is as follows. So in order to define so the important quantities are integrals of universal differential forms namely the kappa i's, over, well, n of A is a submanifold of S of Rn, but let's just think of it as a current. In fact, it's a submanifold, so let's say it's an integral current. In fact, let's say it's a Legendrian integral current in SRN. In fact, let's say it's a Legendrian integral cycle. It has boundary 0, empty boundary. In fact, we even say it's a compactly supported, but let me stop here. Legendrian integral cycle. Okay, so maybe yeah. So maybe the observation is that the concept of Legendrianness makes sense for currents simply as follows. So I've got some current, say it's an integral current of dimension n minus 1 in SRN. Okay, and I restrict it by alpha, and if that is the 0 current, that's the same thing as saying that T is Legendrian. Okay, so again, as you recall, in the language of currents, this just means that T annihilates every multiple of alpha. The exterior T annihilates when paired with any with the wedge product of alpha with any n minus 2 form. This always vanishes. Okay? So if T is given by integration over a submanifold, this condition is precisely equivalent to this condition here. Okay? All right. Very good. So All right, so good. So let's so in some sense, yeah. So yeah. I have to say I have no idea how much time I have. Well, I know I've spent a half an hour or so, but I don't know what I can't remember the last time I gave a 2-hour lecture. And I don't know what 8 hours means either. So anyway, we'll figure this out. Anyway, in any case, please feel free to.
You should have a break in the middle, so.
Thank you. Thank you. Okay. So I've just given you a sort of a very rapid introduction to sort of the classical Steiner formula for smooth domains. Let's see, a few more little remarks. And as I say, I've given, as I say, this fancified approach to this subject, which I promise to make to justify shortly. Yes.
Maybe this is obvious. So
Yes.
Is alpha the like form on the tangent bundle?
It's a one form.
Oh, okay.
So it's derivative. So basically if I look inside the whole tangent bundle, identify with the cotangent bundle, it is the sort of this canonical primitive of the symbolic form. It's differential as a symbolic form. Okay? Yeah. So good. Okay. So hey, here's another little principle. So I just discussed this for smooth domains. As I mentioned, there's also a version of this thing, probably the classical, one of the oldest version of this, maybe the oldest modern version, whatever that means. Due to Hermann Weyl, this tube formula also holds for compact submanifolds, smooth submanifolds of Euclidean space, at least for small radii, of whatever codimension. But, from one perspective, I'm kind of fond of these general principles, especially if they're not literally true. Okay, so everything is a domain. In this subject, all objects are just domains. You can think of them as being somehow bound, so these little thick pieces of Euclidean space. Well, why? If I have some tube in space, some curve in space, for example, and I want to do a tube formula around it, well, so there's C. I can still think of n of C. Well, now this is some manifold of so now V is perpendicular to the tangent space. Okay, so again, this is inside SRN. Okay, and you can do exactly the same procedure. So now, of course, the fiber at each point is a little circle. Okay. But another way of doing that is maybe before we go all the way out to radius r, one thing we can do is just go out to some tiny little radius epsilon, okay, and then if I go out, so c sub r, I can think of it as c sub epsilon, r minus epsilon, so r minus epsilon tube around the epsilon tube, and now the epsilon tube is actually a nice domain. It's a tube, okay. And furthermore, this guy here, well, it's in some definite sense, well, you all are geometric measure theory people, it's flat close to n of c epsilon. So let's do it. Just my little. How do you like that? Okay? Yeah, I mean, so what's the point? It's like you can even write. I mean, it's trivial to write a little chain whose boundary is the difference of the two. Okay. So in other words, first of all, the whole argument goes through as before. Okay. And if I'm concerned about the geometry, I can think of it in this fashion. Okay. What else? Yeah. Okay. Yes.
For the integration, so n of c, we take the vector v unitary vector.
Yes, that's correct. That's right. So I intended to express this way. So this, yeah, that's right. Okay, so yeah. So anyway, I guess I'm a little nervous. Let me pause here and tell you technically what I want to do in these lectures, which I've omitted up to this point. Okay. So I think I'm slightly ahead of schedule, so I'm gonna try to relax here, and let's just recap, just see what we've been doing here. So I started off by talking about this Principal Kinematic Formula. Let me write that again because it's sort of our big deal. Okay, there it is. All right. So now I'm regretting that I didn't manage to display that slide. Let me read it to you. So all in its proper time. So as I said, somehow this idea from the point of view, if we start from this formula, the idea is the basic question is, well, how regular must A and B be in order for such a formula to hold? Okay. Now, so from the discussion we've just given, we can see that in some sense the question becomes, well, these things here are some kind of generalized curvatures in that case. Well, if A and B are domains, they're actual curvature integrals. They're integrals of certain invariants of the second fundamental form. Okay? So another way of viewing this question is, well, how regular must A and B be in order to admit these curvatures as definite quantities? Okay? And this was the question that Federer intended to address, okay, in his famous 1959 paper. Okay? Now, from this perspective, just from the perspective of generalized curvatures, one might ask, well, why do I care so much about this formula? Why am I making this formula the centerpiece of these lectures, which indeed I am? So for this, I guess I intended to, as I say, open with an appeal to authority, right? Which I guess, as I get older, I start to appreciate the need for when I'm talking to my kids, for example, So anyway, let me just pages, first 2 pages of Federer's paper says so he talks about the Steiner formula, he talks about the Gauss-Bonnet theorem, okay, we'll talk about that in a bit, and he says all these classical investigations involve related geometric and measure theoretic curvature properties of various special types of point sets. The search for a general theory is an obvious challenge. Those subsets of n space which are to be the objects of such a theory must be singled out by some simple geometric property. In Federer's case, he was talking about the sets with positive reach, which he introduced in this paper. Among these objects must be all convex sets and all regularly embedded manifolds of class 2. The curvatures attached to these objects should have global aspects of Minkowski's Zermos integrale. Those are these objects, these quantities, when A and B are convex, yet be determined by local properties. Hence, it seems reasonable that they should be measures. And indeed, in the case of sets with positive reach, these guys turn out to be total variations, if you will, of certain signed measures associated with A and B. Okay. Neither the definition of the curvature measures nor the statement of any important theorem about them may contain explicit assumptions of differentiability, because arbitrary convex sets are to be admissible objects. So as you know, the boundary of a convex set, a general convex set, well, it's sometimes a useful fiction to think of such a thing as being twice continuously differentiable. But as you know, that's certainly not the case. That you can have convex polyhedra, where these very sharp angles, and there are also other possibilities. You know, if one can think about, for example, convex sets where the curvature, in some sense, is distributed in some fractal fashion. Okay, so for example, supported on a Cantor type set. Okay. Yeah, whatever differentiability may be required for an auxiliary analytic or geometric or algebraic argument must be implied by the geometric properties. And now, Federer's testimony, not mine. Of course, in order to be worthwhile, such a theory must contain natural generalizations of the principal kinematic formula and of the Gauss-Bonnet theorem. Okay, so anyway, Federer believed it. And I guess, in some sense, what I want to do is introduce what I feel is sort of the correct formalism that extends these constructions of Federer. This is something that's been worked out slowly over the past 20, 25 years, but more recently has come to fruition in a particularly incisive way. But the theory, there's a general theory that I'm going to lay out, but the general theory has many, many holes in it. Somehow one can define it under a rather general conditions, these quantities mu I. And in fact, in more general spaces and under more general group actions, things are quite suggestive. And yet, somehow the transition from the basic formalism of the definition to, well, actually the principal kinematic formula, actually have a proof of the kinematic formula, is problematic. Okay, so let me just, as I say, lay out what is the technical aim of these lectures. With, I hope, many side excursions, I think, because, as I say, this is a vast can of worms. So this technical aim has recently been accomplished by work of myself, Dusan Pokorny, and Jan Rataj. Okay. So yeah, let me just say it. So the first thing is that the positive reach case can be approached in exactly this fashion I described before. Okay, so instead of a smooth domain, you can substitute a set with positive reach. Let me recall you what that is. So A is positive reach, if we will, means there exists a positive R naught such that if the distance from X to A, say, is less than R naught, then there exists a unique point P in A such that the distance from X to P is precisely the distance from X to A. Okay. So this is so-called unique nearest point projection. So here's sort of a picture of a representative set with positive reach. So here's the point. It's close. I can project it to that point. There's X. There's P. All right? And so in some way, these things are exactly, what they are, in some way, I can replace this A with a little tube, as long as that little tube has some radius less than r naught, which is the reach of A. That tube is actually sort of a nice, smooth domain. Well, almost smooth. It's actually not C2, but C11, has a Lipschitz normal. And so from the geometric ratio theory point of view, there's no difference with C2. Okay. And so somehow with this perspective, all this other stuff goes through. Okay? Now, there's this really nice characterization of PR sets. Here's a theorem from, I think, again, from the 80s, due to Norbert Klein-Johann and Victor Bangert separately. So it says the following. Suppose I have got let's just keep things simple. Suppose I've got A compact inside Rn. So this set has positive reach if and only if the following is so. There exists a function f which is semi-convex. What does that mean? It means there's a smooth function plus a convex function. Maybe locally. It doesn't really matter. Okay, so it can be, a function be semi-convex if you can express it as a smooth function plus a convex function. So for example, obviously convex function is such a function, or a smooth function. Or, maybe something like the absolute value minus x squared. That's a sort of prototype semi-convex function. Okay, so and what's called a weakly regular value C of f. What does that mean? That means precisely, so some generalization of regular value, of course. So C is weakly regular value of f if, well, let's see. So any smooth function, of course, is differentiable. Well, okay. Any convex function is also differentiable in a certain sense, in a certain set-valued sense. So, as you may recall, there's a sub-differential associated with any point in the domain of a convex function, namely. So the sub-differential is basically the set of all say linear functionals, such that the associated linear approximation is less than the given function in the neighborhood. Okay. So if I write this as g plus h, I can take the so-called df at x. I'll call that the regular derivative of x plus dg of x plus dh of x. Okay. So what else? So yeah. So maybe I should say a little bit more about this. This is so. For example, if h of x is say x squared, then dh of x. Well, if x isn't 0, then this is just the usual derivative, usual gradient. And at 0, what is it? It's a well, strictly speaking, it's a set. Here it's the unit ball. Okay, so in other words, if I've got this cone here, I just look at all these tangent planes or support planes at the cone, and all those, each one corresponds with some linear function. Those linear functions are precisely the dot products with with unit vectors, or vectors of length less than or equal to 1. Okay?
You meant H equals to the absolute value, right?
Yes, thank you. Okay. So anyway, so C is a weakly regular value of the semiconvex set, of the semiconvex function f, if the following is true: whenever I've got a sequence of points, x1, x2, and so on, and these things decrease to 0, and the VI, I've got elements, I've got subgradients in these at these points. Under these conditions, the VIs don't converge to 0. In other words, the subgradients at values of C, at values slightly larger than C, are bounded away from 0. Okay. And finally, what's the characterization? So I haven't referred to the set A yet. And so A is just the sublevel at that level, at that weakly regular value C. Okay? All right. So yeah, so what's the point here? So in other words, as I say, the distance function from my semiconvex set, from my PR set, is such a function, but it's not necessary to take that particular function. I might take other functions with level sets like this. You might have these sharp corners like that, as long as they're always pointing out, so to speak, as long as the singularities are always somehow outwardly convex. That's what's guaranteed. And what's necessary is that, well, these gradients out here, they never somehow collapse. I guess these cusps, things like that, whether inside or outside, are not permissible. Okay, at a point like this, you might have a 0 subgradient. Okay. So anyway, so that's this guy. So what's the theorem? So Federer was able to prove, first of all, construct these mu sub i's for sets with positive reach, and secondly, in sort of the longest, most difficult part of his paper is the proof of the principal kinematic formula. So for us, we're going to, whoops, rats, there we are. Let me just see if I can make this statement. And then we'll take our break. So first of all, we're going to introduce this class of functions. Well, it's not our class of functions. It's a very, in some sense, in geometry, very familiar class of functions, so-called DC functions, differences of convex functions. Maybe. Let's just avoid certain issues, just look at functions that are locally expressible as differences of convex functions. Okay? So then you could say there's this notion of subdifferential or weak differential for a difference of convex functions. Well, I'm going to caricature it slightly. I'll correct this later. The definition I'm about to give you depends on this particular decomposition. However, the decomposition is certainly not unique. So I'll define this as the difference of these two convex sets. So what does this mean? This, like you might say, this is the Minkowski difference, if you will. So these are both convex sets. This Minkowski difference is a new convex set consisting of all differences of vectors of elements here and elements here. Okay? Okay. And so now, again, you can define what's meant by a weakly regular value of some function h, which is dc. as before in these terms. Okay. Under that conditions, we call this set we call it a WDC set. So weak difference of convex functions set. Okay. So these sets are, are strictly larger. It's a strictly larger class than the positive reach sets. Okay. So, so in other words, what's clear underneath that board is that any smooth function, in particular, is locally DC. If I just add some sufficiently large quadratic function to it, then what's left over is going to be concave. All right. So semi-convave. So these guys contain semi-convex. So these guys here, these WDC sets, are a strict generalization of PR sets. So the theorem basically of Jan Duchamp and myself is that, if I've got A and B inside Rn, they're WDC, then we can define these mu i's and finally the PKF holds. Okay. So in other words, what we have, is sort of a systematic way of dealing with so-called inside corners. So these sets with positive reach, or as I like to call them, semi-convex sets, for the obvious reason. I will slip into that terminology frequently. I'm sure I already did. So a semi-convex set can be quite singular, but somehow all the singularities are sort of outward pointing. They're convex type singularities. You can have concave parts, but the concave parts are in some definite sense required to be quite smooth. Okay? These DC sets, WDC sets, that difficulty is removed. You can have sort of lots and lots of these so-called inside corners. I mean, I guess the need for such a theory has been felt for some time. For example, not only does this formula hold for, say, convex sets, but also it's been known for a long time to hold for finite unions of convex sets, where you have certainly some kinds of inside corners, okay, in some ad hoc fashion. So this is maybe the first class that's been identified since Federer's days, where we can deal with these inside corners in a really systematic way. Okay, so. Along the way, we'll see a lot of issues. So one thing, I guess the main point being that, in my firm opinion, this is by no means the definitive version of this theorem and of this theory. There's some really unimagined and perhaps in some definite sense unimaginable class of sets to which this applies, and I hope to talk about that. Sort of the dimensions of what's not known and what we'd like to get maybe towards the end of this series. Okay, right now let's take our break. Okay, so I guess in this last section of today's talk, I want to just try to address this question. So what is this N of A thing? So I guess when A is a smooth domain, yes, we know what it is. It's this manifold of outward unit normals. If A is positive reach, by the way, I didn't quite tell you this, but again, there's something completely analogous. So for example, here's my nice set with positive reach inside the plane. Okay. So one thing you can do is again, because it's semi-convex, somehow there's not a unique normal at every point of the boundary, but there's nonetheless some collection of vectors that you can characterize as outward. So maybe two ways of characterizing this thing. So n of a, set of all, say, x and v, again, inside the sphere bundle, where I guess x, say, belongs to the boundary of A. I'm going to use this word for the topological boundary, and say v inner product with W is non-positive for all tangent vectors to A at x. Okay? So tangent vectors are defined in the obvious way. Just take sequences of points converging to x and renormalize them and take the corresponding cone. And this is so these guys are somehow the unit vectors of the dual cone to the tangent cone. Okay, so another way of viewing it makes it look sort of nice. Well, again, because there's this nice projection. So let's take pi a, say from a r naught. So there's some, as I say, there's some small neighborhood of a for which there's a nearest point projection. So there's, I'll call it pi sub a. Okay, and so now let's fix some r that's less than r naught and look at the boundary of a sub r. Let's call it m sub r. So this guy here is actually, as it turns out, is a nice C11 hypersurface. Okay. And it's, I guess if Rn is oriented, it's oriented. I can think of it as a current. Now let me take the following map. Let's take, let me call it phi. Phi a maps. It takes. It's going to be, say, pi a of x, and then x minus pi a of x normalized. Okay. So what is it? If I'm here, there's x. So this map here under phi is mapping to, well, the first component is there, and the second component is the unit vector in that direction. Okay. And it turns out that phi sub a maps m sub r diffeomorphically onto some object inside SRN. Okay, so this is a nice one-to-one mapping. It's actually by Lipschitz. So this is actually a nice Lipschitz submanifold of the sphere bundle. Always of dimension n minus 1. Okay. M sub r is oriented. This is oriented. I can think of it as an integral current. Okay? And again, it is, well, compactly supported. It's a cycle. Boundary is 0. Yeah. So let me, I'm going to, so maybe strictly speaking, so for us, let's see. So for us, what is n of a? We'll define it to be this current. I'm a little bit perverse, maybe. I don't know. It's like star is always used for covariant functors whenever possible. I don't know, not sharp. Anyway, so I think of this current like that. So here's the fancified version of n of a. It's a Lipschitz submanifold, but I want to think of it as a current. It is compactly supported. It's a cycle. Its current theoretic boundary is 0. It's Legendrian. Again, if I evaluate it against any multiple of the contact form, I always get 0. Okay, so these are some conditions. Okay, so I want to understand a few more things about it. One thing that's true of this thing is that the Gauss-Bonnet theorem holds. So what does that mean? So I guess, as you recall, we define this this invariant form kappa 0 is just the volume form of the sphere pulled back. Okay, and classical differential geometry says that if I pull back this form by the Gauss map and integrate it, I get up to scale the Euler characteristic. So, as usual, I'm going to drop the scale. So, classically, mu 0 of A, again, what is that? It's defined to be the integral over n of A of kappa 0. Okay. This is equal to, well, okay. I'll put it in now. So it's the area of the sphere, which I'll just note this way, times the Euler characteristic of A. Okay. So that's the theorem of Federer for sets with positive reach. Let's just see one way we can prove this thing, maybe even a little bit more, maybe in some slightly fancified way, as I said. So, so if I look at mu 0a, so what is it? So basically, it's the integral of n of a of kappa 0. What is kappa 0? Kappa 0 is, let's see here. I guess I need notation. So SRN. Let's project it to the sphere here. Let me call this P. So kappa 0 is just the pullback of the volume of the sphere under that. That's okay. Now, another way of saying this is as follows. Let's see. Yeah. So let me just say it, and maybe we can get to it later. So what I want to do is, suppose I take n of a, and I slice it by p at v. Okay. So this thing is, I've sliced this n minus 1 dimensional current by a map into n minus 1 dimensional space. This is a 0-dimensional integral current, so it's a sum of point masses with multiplicities. And I guess, well, what is this? What am I saying? Let me write it this way. So I can write this over the sphere, as an integral over the sphere like this. Let me use this notation number for just the sum of those multiplicities. Okay, so this is, okay, I'm sort of fancifying everything. I think there's a purpose, but hopefully it'll come out soon. Okay, so this number actually is a constant. This constant is the characteristic of A. I mean, just by the constancy theorem, this has got to be a constant, and that's how it works. Okay, so so what is this thing? So let's draw a little picture of this current here. So maybe here's V, and let's be let's take A to be a smooth domain. So what is this current? So I guess this current consists of, like in this case, 1, 2, 3, 4, 5 points corresponding to these outward pointing null vectors, like so. Okay. So one thing you can do is look. Let's just So in fact, what we're saying is that the multiplicities associated. If we sum the multiplicities associated with these 5 pointed vectors, I'm going to get the Euler characteristic of A, which in this case is 1. So what are those 3 multiplicities? I guess in this case you can see what they are. We get plus 1, plus 1, plus 1, plus 1, minus 1, minus 1 here. Okay. Well, actually, this picture is, from a certain point of view, it's a certain form of sort of reduced Morse theory, if you will. Okay. So let's even be a little bit more specific. Let me think of this. let me call it h sub minus v of x, the height function. Well, I guess in this case it's the depth function, right? The height function in the direction minus v. Okay? So according to classical Morse theory, what I do is, well, one way I can oops, I want to maybe just make this a little bit more interesting. Drop it down a little bit. So there's another minus one. Okay. So if I start, say, looking at sublevel sets of this depth function, that means all the points in the half space above whatever level, above whatever height we choose. Well, the Euler characteristic of the part of A that sits inside that half space, let's see, so this space, I'll call this half space, if this is h sub minus v of x is t, I'll call this h sub vt here. Okay. So in other words, what I want to do here is, well, I mean, yeah. So what I want to do here is somehow pull this identity apart in a little way. I want to look at this quantity, but I want to look at the individual terms and see what they mean. Okay. So as I say, well, 1 plus 1 plus 1 minus 2 minus 1 minus 1 is 1. Indeed, that's this multiplicity here. That's 1 as expected. But we can say, as I say, a little bit more if I look at those multiplicities that lie in each half space. Well, what I'm going to get is, if I sum them up, what I'm going to get is the Euler characteristic of the part of A that lives in that half space. So, for example, I've got one point here. I've got just one component. Euler characteristic is 1. I add 1 here, there, and there. I get 1 more. By the time I get down to here, well, 2 of these lobes have become combined. This minus 1 kills these guys. So these guys here. So if I write, in other words, n of A, p v. So what does it look like? So it's a sum of some, say, multiplicities. Mi. I'll write this way. Say xi v. Okay, so some finite sum like so. What are these guys here? These guys here are what I like to call the Euler Morse index of the depth function in the direction v at xi. Okay? So in other words, so as you recall from classical, the basic set of Morse theory is the following. I've got some function on a manifold. In this case, it's a domain. There's a nice generalization to the domain, to domains. It works. I've got some manifold. I've got some smooth function on it. I've got a non-degenerate critical point. So it's got some Hessian there. I look at the signature of the Hessian. So it's got some number of positive eigenvalues, some number of negative eigenvalues. I just count the number of negative eigenvalues, and what happens is I pass from one level, from below that level to slightly above that level. Topologically, what happens is that we add a cell of dimension equal to that index, the number of negative eigenvalues. Okay? So topologically, what does that do? What does it do to the homology groups? It either adds one element to the ith homology, or it kills an element of the I minus first homology. Is that right? Anyway, plus or minus 1, I forget. So but in any case, the net effect is to change the Euler characteristic by minus 1 to the I. Okay? And that index, which for manifolds is plus or minus 1, is what I call the Euler Morse index. Okay? So here we are. So yeah, so in fact, Gauss-Bonnet works, but furthermore, we might have this sort of enhanced Gauss-Bonnet. So maybe the slicing, of course, it's a little bit problematic for all V's, but it works for almost every V. So for almost every, say, v and t, say, in the sphere cross the line. Yeah, question. Okay. If I look at, let's see, if I look at HVT, okay, so H, let's see, I better call this H minus VT. I hope I don't get mixed up with my signs. I probably will. Okay, so I look at a certain half space. I intersect it with A. I take the Euler characteristic of that thing. Okay, and this thing should be equal to the sum, basically the sum over, say, x in H minus VT. Look at all points in that half space. Of, well, what? I'm going to take, well, I guess here's how to write it, I guess. So I'm going to slice n of A by P at V, okay. I'm going to restrict to H minus VT. In other words, I just look at those atoms, or strictly speaking, I guess. This guy lives upstairs in the sphere bundle, so pi is the projection. Pi will always be the projection of a bundle. So I look at those points that sit above points of this half space. I look at the total multiplicity, and that's what I should get. Okay, and that works. That works. You can do this kind of basic Euler-Morse theory with positive reach. Certainly works for domains. It's all good. Okay. So that's one thing. So yeah. So let me mention. Yeah, I mean, and somehow, yeah. So let me state this. That kills me. This Blackboard won't go. Okay, but no. Okay, so let me state a theorem. So just sort of set up. So basically, yeah. So this is an old theorem of mine. From 94 or so. Says this. So yeah, it's sort of a funny statement, but here it is. So let's let A some compact set, and let's just suppose, I don't know, let's just suppose that almost every Euler characteristic, that the intersection of this set with almost every half space has a well-defined Euler characteristic. Okay, I'll try to state this thing in more formally sensible terms in a minute. Okay, so then there exists at most one integral current in here of dimension n minus 1 such that, first of all, it's a cycle. Second of all, it's Legendrian. Third of all, its support is compact. And fourthly, if I take T, I slice it by the projection to the sphere at V, and restrict it to this half space here, and count up all the multiplicities, then that's this thing. And this should be true for almost every V and T. Okay? So that's the theorem. That's the theorem. So in other words, it's this sort of minimalist description of what the normal cycle of an object should be. Now, let me just say something about it. I mean, obviously, this condition here is a little bit hokey. So somehow, in practice, what happens is maybe you've got some object and we'll have some recipe to produce some integral current, and lo and behold, it will have this property. Okay, and that's fine. Formally speaking, this formulation is not needed. Really, what's being said is that if you have an integral current of this type, and almost every one of these expressions is 0, then the current is 0. Okay, so let me write that. So perhaps. Yeah, so if we just discard this, let me write a formally sensible statement. If I've got such a thing, and this is 0 for all those guys, then T is the 0 current. Okay, T is the 0 current. Yeah. Okay, so in other words, as I say, what we got is a formal characterization, a formal criterion for what the normal cycle of some object should be. Okay, now, and indeed, this is this, as I've just shown you, at least in rough terms, the normal cycle of a semi-convex set, a PR set, positive reach set, satisfies these conditions. The normal cycle of a PR set is this. This does characterize that thing. Okay. And so now, in some sense, the whole idea is to widen the scope. Let me mention first of all one thing that sort of that we do not know. So just as an emblem of what terrible shape the general theory remains in. So going back to the original version, So I've got this theorem in two versions. There's a crossed out version and the uncrossed out version. Okay, in the crossed out version, we define n of a to be this t. Okay. All right. So one thing we don't know, if we just have such a current, suppose somehow heaven hands us this current associated with this set, and that's great. But one thing we don't know, for example, if I take some little diffeomorphism, some little twisting up of Rn, okay, then there's a natural way to push forward T by that map. Well, we don't know that this pushed forward current is associated in the same way to the pushed forward set. Just don't know. It's just completely, So in some sense, I guess one way I like to say this is that the proof of this theorem is somehow too easy, as we'll see next time. Okay. It tells us too little. Okay? All right. So the way we're going to construct these things for DC sets, so that in short is the procedure. In practice, whenever we can actually just construct these things, yes, this sort of transformation property will hold. And indeed, that's going to happen here. But that's the general thing. So let me mention another thing. So as you recall, so our goal anyway is I'm going to construct n of a for DC, and I guess as I say, maybe let me just to pursue that last line of thought. So even if we have this n of a characterized in this way, we sort of don't know how to manipulate it. I mean, in general, we can't manipulate it. We just can't. We don't have a calculus for it. So much less do we have, for example, if we have two of these objects, I want to do something like a kinematic formula for them. So as I'll describe maybe tomorrow, again, there's I've got to move this one into some position. I want to produce a normal cycle for the intersection. That's what the proof of the kinematic formula will boil down to. That's another difficulty altogether, maybe another altogether different level of difficulty. Technically, in this abstraction, we're so far from being able to approach that. It's, as we say in the States, it's not even funny, okay? So, but for DC, we're going to be okay. Yeah. So one way we're going to do it, as I say, we're going to view DC or I should say WDC. So what are these things? These guys are sub-level sets of DC functions, as you recall. So again, recall from the last hour, A is in WDC means, by definition, A is a weakly regular sublevel at for some DC function. So now, likewise, you know, if A was semi-convex, positive reach, okay, then again, as you recall, the same thing is true where F is semi-convex, same list of conditions. And so what do we do? In fact, in this case, here's my A. The way we constructed the thing basically was we looked at our function f, semi-convex function f. Might have these singularities, but for the slightly larger values, so here's f equals say r, which is say bigger than c. For these other values, these things are nice, well, semi-concave domains, if you will. Okay. These guys out here, because of the regularity condition, locally they look like subgraphs of semi-concave functions, semi-convex functions. Okay, so one thing you can do is just let's look at the graph of the differential of f. Okay, in the semi-convex case, this is again just as well. It's just some small variation on the normal cycle in a way. So if f is semi-convex, then this here is some Lipschitz submanifold now of the full cotangent bundle. Okay, so this is a nice thing. So, for example, probably the simplest example is, you know, if my function is actually convex, say the absolute value function, what's the graph of the subdifferential look like? It just looks like this. So here's -1, here's +1, and then you sort of fill in the gap here. Okay? So the subdifferential extends from -1 to 1 there. Okay, so one thing you can do, actually, is that, well, now n of A, I can construct in the following current theoretic fashion. I'm going to view this as a current again. I'm going to call it this, blackboard df, as a current. Now it's a current of dimension n inside the full cotangent bundle. So what can I do? I'm going to slice this current by f composed with the projection at some r, okay? And I know that all these things, because of the weak regularity condition, all these guys are the fiber components are all bounded away from 0. So I can, if I normalize, so I take nu, say takes t star m minus the 0 section out to, Rn, out to sRn. So xv goes to xv over v. Okay, so this is well defined out here, at least for values of r slightly larger than c. I take this limit, like so. And that works. Okay, again, maybe in some sense this is like too fancified for the positive reach case, but it works. Okay? So this is exactly what we're going to do in the DC case. All right? So before we can do that, I need to state a theorem, sort of companion theorem to this one. theorem A. So this is due to me in like 89 or so, and then the updated version due to Bob Gerard in 05 or something, I think. So Bob and I are really enthusiastic about this theorem, but as Bob remarked, it's like said like somehow to really be enthusiastic about this theorem, you have to have discovered it yourself. So that's unfortunately, hopefully that's not always going to be the case, but so far I'm trying to sell it to you guys. So we'll see how you like it. Okay, so it says the following. So let me state it. Let me state it in Bob's version, which is a little bit more general. So suppose I've got some function. Say it's W11. Let's just say it's defined on all of Rn. There exists at most one integral current now of dimension n inside T star Rn with the following properties. First one, again, it's a cycle. Second one, now here omega is the symplectic form. This thing has got to be Lagrangian. So omega, so if this is Rn cross Rn with coordinates x and y, this is like this thing, standard symplectic form. And what we're saying is that this thing it annihilates every multiple of symplectic form. Thirdly, if I look at the restriction of this thing to any compact set, the mass of this guy is finite. Okay? Okay, and then fourthly, I mean, there are different ways to state the following thing. So, so let me state it in sort of the fancified version first. So if I take t, so for almost every x, if I take t and I slice it by the projection to the base space, okay. Well, anyway, what's t supposed to be? T is supposed to be the graph of the differential of f. Okay, t is supposed to be the graph of the differential of f. So maybe the first thing to think about before we get here, I will complete this equation before the end of the hour. Okay, but just think of f as c2. Think of t as the graph of its differential. Okay, well, of course it's boundary zero. It's Lagrangian. Okay, this is a version. This is probably the first exercise one should do in the subject. To say this is to say that the mixed second partials commute. Okay, that's so in other words, again somehow the prototypes of Lagrangian submanifolds are somehow the graphs of the differentials. So Lagrangian submanifolds of symplectic manifolds are a big deal in that subject. Here's sort of very, very simple application, but that's somehow, in some sense, the origin of the idea. Okay. Of course, again, if f is c2, this thing's just a graph. I mean, it's just, of course, the mass is finite. It's like just there it is. Okay, there's nothing to it. And finally, I'm going to slice this thing by the projection to the base. Okay, so what should it be? Well, this should just be the differential at x, roughly. So it should be an atom at the point x, comma, df at x. Okay? And now the condition here is just that this should be true for almost every x. Okay? So this thing is well defined because, well, that's sort of the reason I impose this condition, just so that this can make sense out of this one. Okay? So that's that. So that's the companion theorem to theorem A. So questions? Okay. Okay. So definition: if T exists, we call it d at f, and we say that f is, well, an MA function, Monge-Ampere function. So what's the rationale for calling a Monge-Ampere function? I guess the idea is that if I take this current, which is supposed to represent the graph of the differential, so now it's an n-dimensional current living inside this, if you will, this product. Here's the space of points. Here, if you will, is the space of gradients. If I take the volume form on the space of gradients, okay, and contract it against the graph of my differential, what am I getting? Any answers? I'm getting a density which is basically, if I contract against the volume of the differential and push that measure down onto Rn, in the classical case, what I get is some sign measure, absolutely continuous with respect to Lebesgue measure, with density equal to the determinant of the Hessian of f. Okay, hence this funny name. Okay. Okay, and so the way this thing works, the first step in this procedure, yes.
Can you repeat this about the last thing you said?
So the last thing I said, what the justification for the terminology?
You know, about the.
Yeah. Okay. So let me write it. So let's say f is C2. Okay. Then t is just this d of f is just integration over the graph of df. Okay. That's just normal. Okay. So this is just a set of all x df at x. Okay, integration over that. Okay, so now these guys are mapping to some cotangent. Well, strictly speaking, it's a cotangent space. Okay, but so the claim is, so suppose here's how to. So I guess what I'm saying is here's what I said literally. If I take df and I restrict it by, say, okay, so there are two projections called p1. I call that pi to r, the first factor, and I'll call it, say, q to the second factor. Okay, so I'm going to pull back the volume form from the second factor by projection to the second factor. Okay, I mean, so I'm saying it first in the fancified version, then we'll talk about what it really means. Okay, so now this is an n form, this is an n current, this is a signed measure. I push it down to Rn. What is this thing? So what it is, it's the volume of Rn multiplied by a certain density. The density is determinant of d squared f. Okay? So, I mean, if f is actually C2, then what are we really doing here? This is the same thing as this is just the same. In this case, I just take df, okay, and, yeah, that's right. So I take the map, let me put big F at x to be x comma df at x, the graphing function, okay. I'm going to pull back the volume form from the gradients. So, I'm sorry. Right, sorry. So df now maps Rn, say, to Rn star, right? Okay, so now I take the volume form here, okay, and I pull it back by this map. What is this? Well, I guess this is just, I claim this is just, that's that. Or, yeah, that's right. Well, why is that? So, I mean, the point is, I mean, computing pullbacks is formally easy, right? So df is taking x's to y's. So what's y? If I pull back y1 by df, what do I get? I'm getting the derivative of f with respect to the first coordinate. Yeah. Yeah. So if I take df, in other words, again, f is C2, if I pull back the function, say, yi. It's the function df dxi, right? Okay, so if I pull back this form here, so basically, so df star of, say, dyi is what? It's the sum over j df dxi d by dxj df dxi times dxj. All right, so right, so I'm just taking the derivative, right? So I've just computed little d with the pullback here. So now, so this thing here is gotten by, well, substituting this expression for each of these factors. I expand it out. What do I get? That. Okay. So it's just this formal device for talking about. I mean, one way of thinking about it is this formal device for talking about this thing. Okay. And again, of course, the cool thing is that it's somehow well defined. If it exists, it's unambiguous. Okay. Typically, it won't exist. Okay. For t to exist, for d of f to exist, is, well, okay, getting back to the subject of the title of the series, it's a regularity condition. It's kind of a floppy regularity condition, but it's a regularity condition on f. Okay. And if f satisfies that regularity condition, we call the regularity class MA, Monge Ampere. Okay. So I want to say two more things. So let's just talk, I guess, in general terms about the state of this theory. So somehow these MA functions, we understand them maybe epsilon better than these sets that are subject to these currents. Somehow because maybe this. So as you see, in each case, there are these sort of three completely formal conditions, and finally there's one condition that actually ties the current, in this case to a function, in that case to a set or a subspace. Okay, maybe as I mentioned, somehow it's a little bit hokey. The expression hokey, like corny, like weird, just off. So this condition here, the uncrossed out condition, the erased condition, is a little bit weird. I mean, just like, okay, how often do you get such sets? Okay, if you happen to have such a set, I can frame it. But in this case, this condition, I think, is good, solid condition. So that helps matters. One funny thing about this class MA, it contains lots of known functions, like, well, let me state the theorem. So this is due to Pokorny-Rataj from last year. Every DC function is an MA function. Okay, so something already known. But now DC, of course, is trivially a vector space. Okay. MA is not a vector space. We know it not to be a vector space. But it contains lots of vector spaces. It contains, say, W2n, all functions whose second derivatives are nth power integrable. But it's not a vector space. Anyway, so the key to making this whole theory work is first of all this. And then what we're going to do is from this, so since DC is since a DC function is an MA function, it has well, trivially, I mean, because it's locally Lipschitz, it has a differential almost everywhere, but somehow these differentials somehow can be supplemented to get a cycle that is nonetheless Lagrangian. Okay, maybe that's another way of stating this last condition here. Okay, that is, I've got a function, say a W11 function, it's got a differential almost everywhere. And so first thing that can be said is, well, if I look at the graph of that differential where it exists, that's a nice rectifiable current. Okay? Not that the differential is Lipschitz or anything, but the graph of the graph is a rectifiable current. Moreover, it can be somehow supplemented by sort of vertical pieces that don't appear to the projection, in such a way that, so all the holes have been filled, I kill all the boundary, and second of all, it's still Lagrangian. And third of all, I haven't just exploded the mass locally. Okay? So that's what that says. Okay, so anyway, so what's the procedure? I guess I erased it anyway. So the procedure again is as before, somehow to, if I've got, say, now a WDC set, which now is some kind of jagged thing like this, maybe, and it's a weakly regular DC value, well, all these nearby objects, sublevels, those are like maybe regular DC domains. These things that look like, locally, like subgraphs of actual DC functions if I rotate, okay? I can construct normal cycles for these guys. Normal cycle for this guy will be the normal cycles for these guys from D of F. Okay? In other words, I've got a graph of the derivative. All those gradients, of course, are somehow supposed to be normal to the sublevels or the levels, okay, in some virtual sense, and the formalism basically all works out. So I guess in some sense, I guess what I'd like to say is this. So I mean, there are all these sort of reductive little slogans that one can carry around, which help me survive anyway. Somehow, it's just in America we call it Calc 3, multivariable calculus, right? So you've got a function on space. You can use that to define smooth hypersurfaces as level sets or smooth domains as sublevel sets, provided you're at a regular value. Okay? You can even construct the normal bundle, outward normal bundle to the sublevel set just by taking the gradient or the gradient field, restricting to the level set, and normalizing. Done. This is a version of that procedure. Okay? All right, so next time what I want to do is give an idea how to prove theorems A and B. And then we'll go from there.